you say they go there and try to understand. Okay. But first, we're going to finish up on the lecture from Wednesday, which had the title was just beyond the ideal gas. We went on to see, to investigate the limitations of the ideal gas and consider what steps or actions could be taken to improve generate equations of state that are better. And the way to do that is to generate equations of state that involve models of molecules that interact, not just totally ignore one another under all circumstances. So they have a long range attractions and short range repulsions. If we want it to be really realistic, sometimes some of those have hardly any of those. We work our way up to the Van der Waals model. Here's just bring this up to date on what we did prior to this. We developed the equation of state that has a long range attraction and has a short range repulsion. The molecules are hard spheres. All the water left today. Oh. They hit. They get more closer to the house. So that's the Van der Waals. These are the soft spheres. If they come together real hard, they get closer together. The Van der Waals model involves hard spheres of fixed size, and that size is I call sigma the diameter of one of the molecules, and this is the equation state. This is the precipitous factor. Now, as these molecules have a size, it would be nice to know something about how big they are. How about real molecules? Do they have a size? That's a good question. In fact, it's so good I wrote it out. What are the sizes of molecules? Can molecular sizes be measured? And if so, how? Anybody have any thoughts on that? Familiar with that? You studied chemistry now for how many years? More than you care to remember, I suppose. So surely you've been taught about, probably know about molecular sizes and where these numbers in the book that we all have, these tables, molecular sizes, where those come from. Any idea? They didn't teach you that, did they? They taught you vocabulary of size, but not science. I hope that's not so, but it probably is, because that's pretty much the bottom line. Well, so I just think this is a question mark for now. If this can be measured, something can be measured. Let's see. One way to measure the apparent sizes of molecules is by studies of collisions between molecules, usually pairwise collisions, the easiest one to study. Now, that's when the forces are felt and experienced. We talked about this slide the other day, or this graphic the other day, how the force and the potential energy are related, one being the derivative of the other, and how these curves look alike, a good deal alike. And as I say, we could use either of these that suits our purpose. Right now, I want to talk about the potential energy curve. And so consider a realistic pairwise collision. what we think just from common knowledge that we all have with us, what we think it might look like. And I want to look at potential, and we know that there's something like this. This is for a pair of molecules. Molecule 1, molecule 2 is separated by this is R, and this is R. So if we start with two molecules, let's say that's all we have in the world, all we're looking at, just those two molecules. And we just, they're at rest, we give one just a weeniest little nudge in the direction of the other, and it starts drifting that way. And that's what happens. Ultimately, if we get to the semi-decimal, they begin feeling one another because of this attractive force, and they will accelerate. This one will start moving. If it was initially at rest, the other move faster, and they'll accelerate. And they'll come together, and then what happens? Well, if you gave just that little teeny nudge, they would move together, and R gets smaller and smaller and smaller. And when you get to this separation distance, they stop. They're accelerating, and then they decelerate rapidly with their brakes on. And they just kiss each other gently and reverse the process. So if those molecules, were the same as it would be in just a modern gas or pure substance, then they would just transfer at the edge of the molecules. Right? Suppose, and another way to think of this is maybe some of you are skateboarders and you do all sorts of tricks and stunts on the half pipe. Suppose this is sort of like a skateboarder's half pipe. And skateboard starts out here just a little teeny nudge. You roll, and these are perfectly frictionless wheels, frictionless surfaces. This is an idealized skateboard and skateboard. Quite half pipe, but an interesting surface. But he would roll along here and roll along here at a very steady speed. But as he started way out there at infinity. And as he gets up here in the vicinity of this other molecules, where he begins to accelerate faster and faster and faster, and then he's back here, he begins to slow down, slow down, slow down, and here it stops. What if he's a hot dog skateboarder and he starts out with kinetic energy like this? This is an energy scale. This is 0. Suppose he gets kicked past it gets going fast. It's an impulse. Now it's moving along pretty fast, steady rate. Coming in from infinity as he gets close up here, he accelerates. It goes even faster and faster, and then what happens? And because this proximity begins slowing down, and it's hard to draw this. Potential energy, kinetic energy, some of them is constant. So if he loses potential, he must gain kinetic. We saw this exactly before we were talking about vibrations, harmonic vibrations. Now, I have this wonderful graphic here that I know will blow your mind. This beautiful drawing of that potential. And we go out very far because it's only in the vicinity of this well. So that's the potential energy I'm just talking about. And you can't see it down there, can you? And as the collision takes place, there's acceleration in this range, and then there's deceleration as you go past this minimum. And ultimately, for a head-on collision, molecules will stop and then they'll reverse back on that process. And the kinetic energy curve looks just like this one, except it's inverted. So I just made one look just like that fact, I just copied on a transparency and left it further. Boom. Now we can see the two of them, and we can scatter these suckers or collide. I hope they're going to try. If I superimpose, I'm not going to waste a lot of time on this. If I superimpose these just like so, where does it turn around? It turns around right here, 0. Now, if I give this guy some kinetic energy, it comes in at a higher. I've got a little mark here down there. If I do that, predict where it's going to come in. Now, it's coming into where does it turn around? Right here. When the kinetic energy goes to 0, that's when they stop. They stop moving and they start backing off. Now, when there was kinetic energy, you say those molecules look like they had this size here. When there was this much kinetic energy, they looked like what? Maybe they have some other size, but they look like they have this size, smaller. More kinetic energy, and then what happens? Smaller yet. More kinetic energy, and then what happens? Smaller yet. You see that? See where this goes to 0 here? It was there when we started at 0 kinetic energy initial. The total energy is just initial kinetic energy, so if it was 0, it's going to stop there. If it's more, it's going to stop. They're going to look small. If it's more, they're going to look small. And small, and small, and small. One way to measure the apparent size of molecules is by using collector beams, like we talked about the other day, where we can have them scattered in vacuum systems, but not anything interrupted, just pairwise collisions taking place. And by studying the dynamics and kinetics and the scattering angles and the like, you can work backwards and calculate the distance closest approach. Calculate other stuff too, but you can certainly calculate the distance closest approach. Collision. Then what do you find? Well, I know this for a fact because when I came to work here back in previous centuries, when I was in graduate school, my dissertation work was on collector beam scattering, where we made these things collide really seriously. Fast and hard. We got a way of accelerating the pants off of molecules and then slamming them into one another. And what we found, yeah, we were doing this to say helium. What we found, it was itty bitty. It was argon, it was bigger, but little bitty. But we were banging together hard. We were going way up that potential fall. When I came to work here, I built that philosophy we talked about the other day, to work with diffusive beams, low temperature beams, room temperature beams, very gentle genteel collisions. They come by and shake hands, say how to do it, and we go on. Really? And what did I find? They look big. Bang them together hard, they look little. Bang them together light, they look big. Change the way you bang them together, and you can map out that curve. So what am I saying? If you're going to determine the size of a molecule, you can't just do it in your head. You've got to measure it in the laboratory. You have to have some experiment that feels the molecule at much like this. Just imagine I have a molecule in my micrometer there and squeeze down on it and measure. We can't do that with molecules. We have to do it with these experiments that give us information in complex form, and we have to back the size up and truth is, just like I showed you on these drawings before, real molecules have no size. And that's a hard thing for students to accept. Probably very few of you ever will accept that, but that's fact. They have no size. They have apparent sizes, and what the apparent size is depends on how hard you squeeze it. If I brought in my micrometer, I didn't, I could, and little steel balls. Like that. Brought it 1 micrometer, a little cutting here. And I put this steel ball here. Now I know it's supposed to be 7/16 inch in diameter, fairly nice and precision ball. And that's 437.5 thousandths of an inch. And I tried, this got all the stiff. It's not a good one to use. At any rate, I put it on there, and you can't read it. I mean, it should be 437.5. I read about 437. Well, my micrometer's probably not that good. That's pretty close. And if I pass this around to everyone in class, and this will fit my micrometer, so you can feel very sensitive when you hit that ball. We'll write our numbers down. They'll all be pretty close together. But suppose that this was a marshmallow. Used to bring marshmallow in, little baby marshmallows. And suppose that we did that, and we put a blindfold on everybody, and said, okay, everybody measure the size of this marshmallow, this calculator, because that's what you do in the laboratory. And then probably fine. Well, traditionally what you would find is that among a group of students of any size at all, probably this one just minimally applies to that criterion. There would be some very, very sensitive souls, very delicate sense of touch. Do this blindfold, and come down and just, ooh, take that for a muscle. And there'd be some macho guys who think that this is more of a secret than a delicate instrument freshman. I know that kind. And they come down, they're blindfolded, they do it, and they keep turning. Finally, they feel something, and they write it down, and one of these things. They find that marshmallow really itty bitty. And the other ones find it, that's the role of the molecules. That is the role of the molecules. Why then do we find these infernal tables of molecular sizes and atomic sizes in all the textbooks? Are they bad? Are they evil? No, not necessarily. They're quite all right. They serve a useful purpose. And at least they would serve a useful purpose if the authors stated that these are the sizes that the molecules or atoms look like when squeezed by the same caliper, not the same measurement technique. I never seen that. These are the sizes I can use them. Does that mesh with the idea of what science is we talked about this past week or so? I think it did. No, it does not. So, real molecules have no specific size. How big they appear depends on how hard the measurement squeezes. What could be easier than that? Understand philosophically. I don't know. All right. But Van Paul's molecules do have model molecules, hypothetical molecules, do have specific size. Why? because that's the model. You play God. Here's the model, rigid hard series. Size is invariant. Therefore, the equation of state that you derive based on that assumption is an equation of state for molecules that have a fixed size. They come together no matter how hard they come together. If they come together, just very, very gently, a little teeny bit, a little microscopic quick, pick up that bang, there's a bigger thing. But they don't get any closer to that. That's the model. Here's a diameter sigma. Now, it's nice to have some feel for molecular sizes, how big they would appear in various scenarios, how big they would appear in a chemical reaction, cell, for example. It's nice to have a feel for that. And the Van der Waals equation is, as weak as it is, can give us some information about that. The B parameter on the bottom molecule, size, sigma. And that's what we saw when we derived the equation. Therefore, should be able to infer about Van der Waals singles from the measured I told you that the A and B parameters are determined experimentally by measuring PBP behavior gases and fitting that to the equation. And so we have numbers for A and numbers for B. And the B derives solely from the size. If there was no size, there's no deficit of volume. The free volume of the molecules moving is not diminished. So it's only giving that molecule some size that led to that B term. So it just makes sense that we should be able to back some information about size from that measured B term. So what is it? I'll ask you to recall. It is, exclude the volume of lower bases due to molecular collisions. What's that? What's the definition? So, let's find out. V is that. It should be Avogadro's number times, and I just have to write some words because there's no symbols to put this in yet. Excluded volume per molecule due to collisions. That should make sense. If it's excluded volume per mole, then it's excluded volume per molecule times Avogadro's number of molecules in the mole. Just true stuff. At low to moderate density, densities, that's N over V. What kind of collisions I've already told you are predominant? Not a gas. And pressure's not real high. Gas like the gas is free. What kind of collisions are most characteristic? You think that probably the most common collision molecules in this room we're experiencing right now is when 10 of them get together simultaneously and try to crunch. Think that's the most common? Or is it 40? Or is it 1,000? How many of them? Oh, it's easy.